Hi guys, and welcome to the first video for Math 8-7. Let's see how it goes. Today we're talking about probability, and specifically we're talking about compound probability, which is the chance that more than one event is going to happen. So if you remember from earlier things that we've talked about probability, do you remember what it means? The probability of something happening is basically the chance that something's going to happen. And we can represent it as a number, and that number would be something between 0 and 1. So if the probability of something happening is 0, you're essentially saying that it's impossible. And if the probability of something is 1, then you're saying that it always happens. So if you asked, I'm going to flip a coin, and what is the probability of getting either a head or a tails, then we would say that the probability is 1, because no matter what you get, it'll either be a head or a tails. If you said, what's the probability that I flip a coin and I get a 6? Well, that's not even a thing that makes sense. So the probability of that happening would be 0. Instead of writing out the phrase, the probability of getting a heads, we can use this other sort of notation. P parentheses heads, or if everyone knows that you're referring to flipping a coin and getting heads or tails, you could shorten that even to saying P and then in parentheses just an H. So this P stands for probability, and whatever's in the parentheses is the thing that you're hoping happens. So thinking about flipping a coin, as long as it's a fair coin, what is the probability of getting heads? Well, there are two things that could happen, and so the denominator for that is 2. And one of those two possibilities is a head. Since it's equally likely to get a head or a tails, the probability would be 1/2. The probability of getting a tails is also 1/2 because there's one outcome that you could get that's the tails out of the total of two outcomes, heads or tails. One of those is tails. If we thought about the probability of getting heads or tails, well, we kind of already talked about that. It would be the probability of getting either a head or a tail, which is something that's always going to happen. We're going to ignore the fact that, like, maybe if you're really lucky, you could get it to land on its side. So the probability of getting a heads or a tails would just be 1. The probability of getting neither a head or a tails, again, we're ignoring the chance that it might land on its side. That would be 0 out of 2 because there's only two things that you could get, and both of them would be a head or a tail. So none of the options are to get neither a head or a tails. I guess we could have also written this one up here as 2 out of 2 because basically you're saying there's two ways to get a yes, and that's out of 2 total ways that you could get a coin answer. When we talk about probability, we're not just talking about getting a head or getting a tails, but we're talking about, like, if you flip the coin twice, what's the probability that you get 2 heads, things like that. So this is called compound probability, and we could write that as something like this, where instead of just writing PH, the probability of getting one head, we could write PH comma H. So that's saying that we're getting a head, and then we're getting another head. We can find this by drawing a tree diagram. So if you think about flipping a coin, you could get a heads, that's one thing you could get, or you could get a tails. That's on the first flip. So there are two possible things that you could have gotten, and they're equally likely. So let's say you did get your head for the first flip. Then what's the chance that you would get another head? Again, that's another 1/2. You could have gotten heads, but you could have also gotten heads, tails. And then it's also important to think about the fact that if you didn't get a heads in the first place, but you still decided to flip for the second time, you could have gotten a heads or a tails for the second as well. All in all, if you're flipping a coin 2 times, then you're going to get 4 possible outcomes. You could have gotten heads, tails, tails, heads, or tails, tails. Can you figure out what the probability of each of these events would be? There's 4 possibilities that you could get. There's 4 outcomes. They're equally likely, right? And so the probability of getting any one of them, like heads, would be 1 out of the 4. This tree diagram is useful because it shows all of the possible outcomes. So you might have been able to think about that easily. But if you draw it out like this, it shows all of the outcomes. And we call this the sample space. So heads, 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 tails, tails, heads, tails, tails would be called the sample space for this example. Now, it's important when we talk about compound probability to introduce the idea that sometimes events are independent and sometimes they're dependent. Independent events means that no matter what your first outcome was, it didn't influence the second outcome. So, like just because you got ahead before doesn't make it any more or less likely that you would get aheads in the second flip. But that's not true for every single situation. So let's take a look at some situations and see if we can tell if they're independent or dependent. Okay. If you roll a 1 on a die, and then you roll it again and you get a 6, what do you think? Does the fact that you got a 1 before affect your likelihood of getting a 6? You might be thinking, no, these are independent events. So every time you roll a die, as long as it's a fair die, each of those rolls is independent. It doesn't matter what you got before. The chance of getting any given side on your next roll is still just 1/6. What if you rolled a die and you got a 1 and you're wondering, well, what if I get another 1? Well, same thing. It doesn't actually matter that you rolled a 1 before. That doesn't make it any more or less likely to get a 1 for the second time. That's still independent. What about if you get an A in math and you like the color red? Well, sometimes with people, it's very complex. So you might think that, I don't know, maybe there's some sort of gene that makes you a really hard worker and it also somehow makes you like the color red. But probably without any data to go off of, I'm going to guess that these are also independent. They probably have nothing to do with each other. But what about this one? The probability of getting an A in math and having good study habits. Now, these don't sound so independent after all, because if you have good study habits, you're probably going to get pretty good grades in all of your classes because you're going to be a hard worker, you're going to get help when you need it. So these are probably dependent. If you told me that you have good study habits, I'd say you're probably more likely to get an A in math. And if you told me that you have an A in math, I'd say, well, it's probably because they have good study habits. These would be dependent. What if you have a deck of cards and you draw an ace, you put the card back in the deck, and then you draw another ace? This would actually be independent because you've put that card back in. There's still the same chances of getting an ace in the second draw as there were to begin with. There's still 4 aces out of 52 cards in total, or 1 out of a 13 chance. But what if you drew out an ace, you put it to the side, and then in your deck that has 51 cards remaining, you're going to try to draw another ace? Well, you might have listened to the way I said that and said that there's only 51 cards left. And you might be thinking that I'm trying to hint that those are dependent. And that's right. So after you've drawn that first ace and set it aside, now there's only 51 cards left, and only 3 of those are aces. So you actually have less of a chance of getting an ace than you did before. But what about if you're flipping a coin and you get another heads after you've already gotten 4 heads in a row? You might be thinking, whoa, like it's really rare to get 5 heads in a row. But actually, for flipping a coin, it doesn't actually matter. Whatever you've gotten before, your next chance is going to be 1/2, no matter what. It actually sometimes seems unintuitive, and this is called the gambler's fallacy. So, for example, if someone thinks that they've uh, lost a bunch in a row on a slot machine, they might think that, well, I'm bound to win eventually. But this is actually not true, and this can cause you to lose a lot of money if you think that. So, independent events, how do we calculate the probabilities? If 2 events are independent, the probability that they both happen is the product of the probability of each event happening. So for example, if we wanted to know the probability of getting 2 heads in a row, which we already drew out before and found was 1/4, you could also just calculate that by saying the probability of getting a heads times the probability of getting a heads. Both of those are a half, and so you can also have seen from this that you would calculate that and get a fourth. Since this is just the same thing twice, you could also write that as being the probability of getting heads squared. 1/2 squared, of course, is 1/4. It's very hard to draw this way. What about the probability of rolling a 1 and then getting a 6? That would be the probability of getting a 1, 1/6, times the probability of getting a 6, which also happens to be 1/6. So we could calculate this as 1/6 times 1/6, or just 1/36. Is the probability of having two independent events both happen greater or less than the probabilities of one event happening? Take a look at the ones before. The probability of getting ahead once is 1/2, but the probability of getting ahead twice in a row is 1/4. Similarly, the probability of getting either a 1 or a 6 is just 1/6. But the probability of those both happening, so rolling a 1 and then getting a 6, is 1 out of 36. So the probability of two independent events both happening ends up being smaller than the probability of either event happening. Does that make sense? If two events are independent, what about the probability that either one of them happens, one or the other happens? Now that's actually the sum of the probability of each event happening. For example, the probability of getting a head or tails is 1/2 plus 1/2, or 1. You'd always get either a heads or a tails when you flip a coin. That's because there's a 1/2 chance of getting a heads and there's a 1/2 chance of getting a tails. So when you add those together, you just get 1. The probability of rolling a 1 or a 6 is the probability of getting a 1, 1/6, plus the probability of getting a 6, which is also a 6. So the probability of getting either of those is actually 2/6, or 1/3. What about rolling 2 dice and getting a sum of 4? Sometimes you have to think about what are all the ways that this could happen. Well, you could get a 1 and a 3, or you could have gotten a 2 and a 2. Both of those would give you a sum of 4. So by taking advantage of this, that we know that the sum of the probability is the way to find the probability of either one or the other events happening, you can actually calculate probabilities for things that are a little more complicated, like rolling 2 dice and getting a sum of 4. It's just the sum of all of the ways that you could possibly get a sum of 4. In this case, there's only 2 ways, and we could calculate each one of these as being 1/6 times 1/6, and here also 1/6 times 1/6, because there's a 1/6 chance that you would get a 1 and a 1/6 chance that you get a 3. Is the probability of one or the other of two independent events both happening greater or less than the probabilities of one event happening? Well, you might have noticed that you went from having the chance of one event happening being 1/2 to the chance of either of these possibilities happening being 1. So you can see that the probability that one or the other event happens is actually the sum. So things get bigger. There's a better chance that either this or that is going to happen. On the other hand, if events are dependent, then it's not so simple to calculate. You actually need to think about what is changing. So let's think back to our deck of cards example. When we pulled one ace out and didn't put it back, but just set it to the side, if we ask the question, what's the probability of getting a second ace in a row, we need to be really careful. The probability of getting that first ace was 4 out of 52. There are 4 aces in the deck out of 52 cards in total, or 1/3. But now that there's only 51 cards left with 3 aces, the probability of getting that second ace is actually 3/51. The probability of getting an ace on your first try and an ace on your second try then is 4 out of 52 times 3 out of 51. We're multiplying here because we're asking what's the probability of getting 2 aces in a row? In other words, getting an ace and getting another ace.